Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will be discussing the aircraft refrigeration cycles, and this is the concluding lecture on aircraft refrigeration cycle. So, in this lecture we will try to solve one numerical. In engineering courses we solve numericals or we give numericals to the students not to judge their computational skill. Here numericals are solved just to have insight of the phenomena, because in numericals you get certain values and these values give you insight of the phenomena. I have taken data for a aeroplane which is moving with 1.2 m velocity, which is supersonic velocity. The aircraft is moving at an altitude of 14 kilometer. Outside temperature is minus 55 degrees centigrade. So, the aircraft is above the troposphere. So, temperature is slightly lower, it is minus 55 degrees centigrade. Ambient pressure is 0.15 bar, it is very low. Cabin pressure has to be maintained 0.8 bar. Please remember that in aircrafts the pressure is not maintained at 1 bar. 1 bar is ideal, but normally the cabin pressure here is taken as 0.8 bar. The ideal pressure would have been 1 bar, but in aircrafts we do not take 1 bar. Normally the pressure inside the cabin is kept approximately 0.8 bar in order to save the energy. Cabin temperature is taken as 24 degrees centigrade, that is ideal comfort temperature. Cooling load in the aircraft is 50 tons of refrigeration. Pressure ratio in main compressor, there are two compressors because it is a bootstrap type of system. The pressure ratio in the main compressor is 5 and pressure ratio in secondary compressor, I mean the gas will again after compression in the main compressor it will get cooled and again it will get compressed. The pressure ratio is 1.3. RAM recovery factor, I will discuss this while when I will solve the numerical, is 0.9. Isentropic efficiencies of main compressor, isentropic efficiency is 90%, secondary compressor 85%, cooling turbine 85%, and temperature drop in first heat exchanger. It means after first compression in main compressor the temperature drop is 65 degrees centigrade. In second heat exchanger the temperature drop is 75 degrees centigrade, and evaporative cooling also contribute in temperature drop of 25 degrees centigrade, and evaporative cooling is done after the temperature drop in second heat exchanger. Now, if we draw temperature entropy diagram for the entire process bootstrap with evaporative cooling, this is entropy and this is temperature. The aircraft is moving with 1.2 m or air is coming towards the aircraft with 1.2 m at temperature 0.15 bar, that is TO. I will keep on writing values on this side so that whenever we have to call the values we can call from here. Now, this is state 0. Now, from state 0 to state 1 the compression takes place, and in order to find temperature at state 1 we will use the equation T1 by TO is equal to 1 plus gamma minus 1 by 2 m square. Here the value of m is 1.2 and gamma is equal to 1.4. TO is, we will write here TO. So, TO by T1 by TO. So, TO is, this is ambient temperature, it is minus 55 degrees centigrade. This has to be converted into Kelvin. So, it will be 218 Kelvin. Now, T1 is, so TO is 218 Kelvin. From this equation we can find the value of T1 as 281 Kelvin. So, here we will write TO is equal to 218 Kelvin, T1 is equal to 281 Kelvin. So, the value of T1 is 281 Kelvin. But in this system there is a RAM recovery factor. Due to RAM recovery factor it is 0.9, the pressure will not be attained as 1, it will be, we will get some state like A dash. The temperature of A dash is equal to temperature of 1, but the pressure of A dash is not pressure of 1, it is less than pressure of 1, and this A dash pressure can be calculated by using the formula recovery efficiency is equal to 0.9 multiplied by P1 dash minus 0.15 divided by P1 minus 0.15. But we do not have the value of P1. In order to find the value of P1, we will have to go for ideal gas relation, that is P1 by PO is equal to T1 by TO raised to power gamma by gamma minus 1. That will give the value of P1 as 0.3648 bar. PO is 0.15 bar, this is 0.15 bar. T1 and TO are with us, and with all these values we will be getting the value of P1 as this. We will note down the P1 also here, somewhere here. So, later on we can recall. So, P1 is equal to 0.3648 bar. Now, after getting the value of P1, we can easily find the value of P1 dash, because the RAM recovery factor is 0.9. So, 0.9 is equal to P1 dash minus PO divided by P1 minus PO. Now, we have the value of P1, we have the value of PO, PO is equal to 0.15 bar. This will give us the value of P1 dash, and this value of P1 dash is 0.3433 bar. It is less than P1. So, P1 dash is 0.3433 bar. Now, after finding out the value of P1 dash, now compression will take place. Now, compression will start from P1 dash, process 1 to 2. Now, during this compression, the compression ratio is given 5. So, T2 is equal to T1 dash P2 by P1 raised to power gamma minus 1 over gamma. Gamma value is already with us. P2 by P1 is 5. Gamma minus it is 0.4 divided by 1.4. Now, T1 dash. So, T1 dash and T1 are same. So, T1 dash can always be taken as 281. So, T1 dash we can write here also 281 Kelvin. So, here 281 Kelvin, it is multiplied by 281 and we get the value of T2 as 444 Kelvin. Now, T2 is 444 Kelvin. As you know, this process is not reversible process, okay. It has certain isentropic efficiency. So, instead of getting state 2, we get state 2 dash. Again, we will use polytropic efficiency equation here and try to find the value of T2 dash. So, polytropic efficiency equation here is polytropic efficiency of compressor, main compressor. Main compressor polytropic efficiency is 0.9 and that is equal to T2 minus T1 dash divided by T2 dash minus T1 dash. T2 dash is not known to us, it is not known to us. T2 is 444 Kelvin, T1 dash is 281 Kelvin. Using these values, we can find the value of T2 dash, and T2 dash is 462 Kelvin. So, now we have another temperature at this pressure P2. is T2 dash, it is equal to 462 Kelvin. After this, the air emerging from compressor is sent to the heat exchanger, and in the first heat exchanger the temperature drop is 65 degree centigrade. So, T3 is equal to T2 dash minus 65 or 462 minus 65 or 397 degree centigrade. So, 3 will come somewhere here. So, this process and then this process 3. So, T3 is 397 degrees sorry, it is Kelvin, not degree centigrade, it is Kelvin. Because temperature drop is 65 degree centigrade, because there is a change in temperature, that is why we did not convert into the Kelvin. So, the T3 temperature at state 3 is 397 Kelvin. Now, again compression takes place in second compressor, and second compressor has efficiency of 85%. 4 and again it is 4 dash, and this is second compressor, this is let us say P4. So, in both the states the pressure is same, but the temperature is different. So, in order to find the temperature at state 4, T4 by T3 is equal to P4 by P3 raised to power gamma minus 1 over gamma. Now, P4 by P3, as it is given in the numerical value itself, it is a pressure ratio 1.3. So, T4 is going to be equal to T3, we can take from here 397 into 1.3 raised to power, this gamma minus 1 by gamma is equal to 1.4 minus 0.4 divided by 1.4, and it turns out to 0.286, and gamma over gamma minus 1 is 1.4 divided by 1.4 minus 1.4 minus 1, here it is not 1, it is 1. So, 1.4 minus 1, it turns out to be 3.5. So, we will next time we will take directly values from here 0.286 and 3.5. So, here it is 0.286, and the value of T4 we are getting here is 428 Kelvin. So, we will write somewhere here T4 also we will write here, T4 is 428 Kelvin. Now, this process is also not reversible process. So, instead of having state here, we will get state T4 dash, and as we did in the case of the main compressor, here also we will use the same formula using the efficiency of the compressor, that is, and the efficiency of the second compressor is 85%. So, 0.85 is equal to T4 minus T3 divided by T4 dash minus T3. Now, T4 and T3 we can take from here, and this will give us the value of T4 dash as 433.5 Kelvin. So, we can write here T4 dash is 433.5 Kelvin. After attaining state 4 dash, the gas is or the air is further cooled, and in second heat exchanger the cooling is by 75 degree centigrade. So, it is cooled up to 75 degree centigrade here. Now, again it is further cooled by evaporative cooling. So, 75 plus 25. So, total is 125, this is 25 degree and this is 75 degree. So, total is 125 degree. So, if we remove or if we subtract 433 minus 125, so T5, now we can write here T6, this is T5 and this is T6. So, T5 is 433.5 minus 75 Kelvin, and T6 is 433.5 minus 75 minus 25 Kelvin, and that is why we get T6 as, yes, there is a correction here that evaporative cooling is not 25 degrees centigrade, we will take it as 50 degrees centigrade. So, I will make necessary corrections here. So, here I have modified the value of evaporative cooling, it is 50 degrees centigrade. Earlier it was 25 degrees centigrade, now I have modified it to 50 degrees centigrade. So, if it is 50 degrees centigrade, then T6 we are going to get, it is 50 degrees centigrade, 50. So, T6 we are going to get 308.5 Kelvin. So, now T6, T6, T4, T5, T6 is equal to 308.5 Kelvin. Now, air available here shall expand, but pressure we do not know right now. We know the pressure ratio between this and this, pressure ratio between this and this, but absolute pressure at this 0.6 is not known to us. So, in order to find this pressure at 6, P6, P6 is the pressure at state 1 dash, pressure at state 1 dash, that is 0.3433 multiplied by pressure ratio 1 dash to 2, 5 multiplied by 1.3, and that is going to be equal to 2.23 bar. Now, we have pressure at this state and temperature at this state. Expansion will take place and it will be expanded up to 0.8 bar. The cabin pressure is 0.8 bar, so it is higher than the 0.1. So, 0.8 bar will come somewhere here, 0.8 bar. So, the expansion will take place from 2.23 bar to 0.8 bar. Still, the expansion turbine has certain efficiency, that is 85%. So, again we will get 7 and 7 dash. So, T7 by T6 is equal to P7 by P6 raised to power again gamma minus over gamma, and from here we will get the value of T7 as 230 Kelvin. So, T7 is 230 Kelvin. Again, this process is not ideal process. So, instead of getting state 7, we will be getting state 7 dash. And now again we will consider the efficiency of the expansion turbine, that is cooling turbine, that is 85%. 85 is equal to T7 dash minus T6 divided by T7 minus T6. We have the values of T7, we have the values of T6. This will give us the value of T7 dash as 241.8 Kelvin. So, T7 dash is 241.8 Kelvin. Now, we have the temperature of air which is used for the cooling purpose, and inside temperature is maintained at 24 degrees centigrade. So, 24 degrees centigrade will turn out to be 24 plus 273 is equal to 297 Kelvin. Now, we have to find mass flow rate of air. So, mass flow rate of the air can be taken as, or can be calculated by just dividing the total cooling capacity, that is 50 ton, multiplied by 3.5 kilowatt, that is total cooling capacity, divided by cooling by 1 kg of air, that is Cp CP 297 minus T7 dash. T7 dash is 241.8. This is the total cooling capacity of the refrigeration system, and total cooling capacity is given in tons of refrigeration. That is why it is multiplied by 3.5 to convert into the kilowatt of cooling, divided by the cooling by 1 kg of air, and this Cp can also be replaced by 1.005, and this will give us the mass flow rate in kg per second, that is 3.15 kg per second. So, that is the one answer we are getting here, that mass flow rate, or it is MA dot is 3.15 kg per second. Power required by the compressor. So, power required by the compressor is mass flow rate of air multiplied by Cp T2 dash minus T1. Cp dt, we have already done that. The power consumed by the compressor can be expressed by Cp dt, Cp T2 minus T1. Here it is T2 dash minus T1 dash. And T2 dash and T1 dash can be taken from here, and Cp value is known to us, Ma is known to us. This gives the power of the compressor as 573 kilowatt. So, power consumed by the compressor is 573 kilowatt. Now, the third one is COP of the system, coefficient of performance of the system. So, coefficient of performance is refrigerating effect divided by the work consumed by the compressor. So, refrigerating effect is 50 into 3.5 kilowatt divided by 573, that is the power consumed by the compressor, and this will give us the COP of the system is 0.305. So, COP of the system is 0.305. So, you have got all the answers, and perhaps the solution of this problem must have given you the clear insight of the phenomena, and now we have numbers, approximate numbers at each stage. Now, in subsequent lecture, we will start with the vapor compression system, vapor compression refrigeration system. In vapor compression refrigeration system, the heat addition and heat rejection takes place at constant temperature or during phase change of the working fluid.